Algebraic identities. The word identity occurs in many different areas of mathematics. It is used in trigonometry, in sets, in functions, and in algebra. In an identity, all coefficients of like powers are equal. An identity must be true for all values of the independent variable. If 3x plus 7 equals ax plus b for all values of x, this is called an algebraic identity. We can conclude that for this to be true, then a is equal to 3 and b is equal to 7. When two expressions are equal for all values of x, then the resulting equation is an identity. All coefficients of like powers of x in an identity are equal. Generally, if ax cubed plus bx squared plus cx plus d equals px cubed plus qx squared plus rx plus s for all values of x, then a is equal to p, b is equal to q, c is equal to r, and d is equal to s. So this is called putting like with like. Also, if ax cubed plus bx squared plus cx plus d equals qx squared plus s for all values of x, then a is equal to c is equal to 0, meaning that the x cubed term on the left of the equal sign does not have a matching one on the right of the equal sign, so we just say a is equal to 0. Likewise, the cx term on the left of the equal sign does not have an x term on the right of the equal sign that it can equate to, so that's just equal to 0. But the bx squared can be equal to the qx squared, and the x squareds will cancel, so b is equal to q, and then the d is equal to s. So they would be the constants. Even though they are letters, we would call them constants in this situation. This property is used to find unknown coefficients in certain equations. Example 1. Find the values of a and b given that 2x plus a to be squared is equal to 4x squared plus 12x plus b for all values of x. So we start with what's given. 2x plus a to be squared equals 4x squared plus 12x plus b. I'm going to do rough work over at the side here. I'm going to work out 2x plus a to be squared. So it's going to be 2x plus a times 2x plus a, which gives me 2x times 2x plus a times 2x plus a, which is 4x squared plus 2ax plus a squared, which is 4x squared plus 4ax plus a squared. So this becomes this, and we have our equals, and then we bring everything else on the right hand side down. So now we can put like to like. So 4x squared will match with 4x squared. The 4ax will match with 12x, and the a squared will match with b. So 4x squared equals 4x squared. Well, they'll just completely cancel out. Then we have 4ax equals 12x, so the x's will cancel. So 4a equals 12, and dividing across by 4, we get a is equal to 3. And then we let a squared equal b. Well, we know what a is 3. We worked that out over here. So instead of a squared, we're going to have 3 squared is equal to b. And 3 squared is 9. So b is equal to 9. Therefore, a is equal to 3 and b is equal to 9. And that's what we were asked to find, the values of a and b. Example 2. If 3t squared x minus 3px plus c minus 2t cubed equals 0 for all values of x, find c in terms of p. So we start with 3t squared x minus 3px plus c minus 2t cubed equals 0. We're going to factorize the first two terms, and hopefully you notice that there's an x common to both terms. So that comes outside the bracket. And usually we would put the x, the highest common factor, first, but in this case we're going to put it second. So we'll have the brackets first. So we have 3t squared minus 3p in brackets, and then the x, which is the highest common factor, is outside the brackets. And then we just bring everything else down. So we have plus c minus 2t cubed is equal to 0. So we're just going to group together in our next step. The only thing we're doing is grouping together the c minus 2t cubed. So in this particular situation, we would consider this to be a constant. I know there's a c and a t there, and they are letters, but there's no x or x squared or x cubed or anything stuck onto this. So we would consider this to be a constant. So on the right-hand side, instead of 0, we're going to have 0x. And that's so that we can put like to like. That's so that we can have the x's equaling each other and then have the constants equaling each other. And when I say constant, I mean the terms with no x's. So we decide to add in the 0x here. So we're going to put like to like. So the terms containing an x, we're going to equate. And the constants, so the terms without x's, we're also going to equate. So we have 3t squared minus 3p x equals 0x. The x's will cancel. So we have 3t squared minus 3p equals 0. We're going to divide across by 3. So we have t squared minus p is equal to 0. So t squared is equal to positive p. So t is equal to the square root of p. And why did I get the square root of p on the right-hand side and t on the left? So why did I do that? Well, I have to go back to my question. I want to find c in terms of p. So p has to be in the answer. So I need I'm going to sub in the t in the next part and replace it with the square root of p so that we won't actually have any t's in our answer. So then I let the constants equate. So I have c minus 2t cubed equals 0. I'm replacing that t with a set of brackets. The brackets is extremely important. And I'm putting the square root of p into the brackets. So I have c minus 2 multiplied by the square root of p to the power of 3 is equal to 0. Now I'm going to rewrite the square root of p as p to the power of a half. This is our indices law 6, which states that a to the power of 1 over q is equal to the cube root of a. So this is on page 21 of your formula book. So this is our indices and logarithms page. So the little formula or the little rule that we are using is this one here, the sixth one. A to the power of 1 over q equals q, the cube root of a. So here I've just wrote it out a little bit bigger. So if we had a to the power of 1 over 2 instead of 1 over q, it would become the second root of a, which is the square root of a. And likewise, if the 1 over q was actually 1 over 3, it would become the third root of a, or the cube root of a, as we would call it. And if it was x to the power of 1 over 3, that would become the cube root of x. So there are just a couple of examples using that law. So going back to our example now. So the square root of p became p to the power of a half. So the square root of p became p to the power of a half. Now that's raised to the power of 3. So this is where another indices law comes into effect. So it's law 3, which is a to the power of p raised to the power of q equals a to the power of pq. And the p and the q are stuck together, which means multiply. So that comes again from page 21. So it's this rule here. So it's the third one down. So I've just wrote it out bigger here. So a to the power of p raised to the power of q equals a to the power of pq. And the p and the q are stuck together, which means multiply. So if you're raising a power to a higher power, the rule is you multiply the powers. So if this was a squared, and it was raised to the power of 3, you would say 2 times 3 is 6. So you get a to the power of 6 and so on. So let's say we had a to the power of a half raised to the power of 3. So raising a power to a higher power, we multiply the powers. And a half multiplied by 3 is 3 over 2. So you get a to the power of 3 over 2. So likewise, if we had x to the power of a half raised to the power of 3, raising a power to a higher power, we multiply the powers. So it'll be a half multiplied by 3, which will be again 3 over 2. So x to the power of 3 over 2. So just a couple of examples using that rule or that formula. So going back to our question, p to the power of a half raised to the power of 3, we're going to do a half multiplied by 3, which is 3 over 2. So c minus 2p to the power of 3 over 2 is equal to 0. And all we have to do then is take the minus 2p to the power of 3 over 2 over the equal sign. So solving for c, we get c is equal to 2p to the power of 3 over 2. And what we've done now is we've found c in terms of p. So we've found c in terms of p. Therefore, t is equal to root p, and c is equal to 2p to the power of 3 over 2 in terms of p.